you're not a mathematician, you're going to faint if you look at that paper. But sort of, so take this as heuristic a little bit. And so what we are going to do is actually substitute for R this quantity minus I gradient of k e to the I k dot R. Because you see, when you take the gradient with respect to k of e to the I k dot R, you get an I R. I minus I gives you plus 1. So you get R, the R vector here, times e to the I k dot R uk, that is psi k again. So, this is sort of in a slightly odd way, again, just trivially the position operator. And then you can do a integration by parts. You have an integral of a differential times an object. So remember, what you have is the integral of this times this, and that is 0 because it's evaluated at the two boundaries of the Breuer zone. And what remains is actually the object inside here times the differential of uk. So integration by part shows us that the application of the position operator to this orbital can be calculated in reciprocal space in this way. And if you take the scalar product, we get the Blount identity for the expectation value of the position operator defined on an orbital W0 that is the integral of psi k in the Breuer zone and related to the integral over the Breuer zone of the periodic part of the Bloch orbital. And the beauty of this definition is that definition is actually remains well defined no matter if the omega 0 are localized or not localized. So we have a working definition of the position operator that is always well defined. And this was actually at the basis of what I'll explain in the sort of second lecture, at the beginning of the second lecture, the Berry phase theory of polarization, because if you want to calculate polarization in a solid, you need to calculate dipole moments or something related to those, and this object is related. And Blount was in great shape, so he decided to extend this not only to the position operator, but to any power of that, and I won't give you the demonstration. Again, those are in the Blount paper, but you see the power, say we are going to care about R square, and that is related to the second derivative with respect to k. And so the bottom line is that in our calculation, where we care about, say, looking at a second moment or a first moment, we have the possibility of calculating those just by looking at the periodic part of the Bloch orbital and taking appropriately these gradients. And there is a sort of key numerical approximation that we are going to take those gradients using finite differences. So if you want to, say, calculate the gradient with respect to k of the periodic part of the Bloch orbital, we are going to construct that gradient in a way that I'll show you in a moment by, say, looking at what are the differences between the periodic part of the Bloch orbital at a certain k and at a very close, very near neighbor. So we have a finite difference vector b that goes from the k at which I'm sitting to a just point nearby in all possible directions, and it's really the building blocks of a finite difference representation of this quantity. Please.
I mean, is that essential, or is that just for ease of use?
Well, so we need to calculate this, and if we are doing a calculation, we don't have any analytical expression for this that we have to integrate. And so, any sort of ab initio calculation in a solid will rely on a discretization of your problem. You're not going to calculate all the states that are infinite, but you're going to discretize your Breuer zone. So I would say it's essential numerically because we need to calculate a gradient, and the way we are going to do it is by finite differences. Okay, and so exactly what I was saying. We sort of do a we do a discretization of our integral, and I won't really go into so the algebra of this problem was really the nightmare. But basically, let me just give you the flavor. That is, suppose you have, let's consider for a moment actually a scalar quantity. U is really three-dimensional vector, but let's consider let's consider a scalar quantity here. That's also what U is. And we want to calculate the gradient. Well, what I'm going to do is I'm going to sit on a k point k, and typically I'm going to choose a finite length, sort of as small as possible, and I'm going to choose vectors that typically have the same direction of the primitive lattice vector. And so by calculating the difference of my function at this little star of k vectors surrounding my k and subtracting f of k, I'm actually able to calculate the gradient. You could actually see this numerically if you were to do a Taylor expansion of f in the gradient, and you would see in the 3 Cartesian dimension that this is satisfied. But as I said, the algebra becomes very cumbersome, so I want just to give you the flavor. That is, we construct these matrices that are scalar product between a wave vector at nearby k points, and then by using finite difference representations, we calculate the gradients, we calculate the second derivatives, and those gradient and second derivatives are related with the value of r and r square. And so this is, you see why the algebra is fairly horrendous. What you end up is the expression for the center, the first moment, and the expression for the second moment, calculated just in reciprocal space, you see, as a function of these n by n matrices that I've defined here. So there's, in the case of silicon, 4 by 4 matrices defined, say, for every k point in a discretized mesh, like the 4 by 4 by 4, 6 by 6 by 6, 8 by 8 by 8 meshes that you use, are going to give me all the numbers that I want. So I can take this expression, do the sum over all the possible n, and I have really an expression of the localization functional as a function of this matrix element M. And then the last part is that I really have to minimize my localization functional. And so what is my degree of freedom? Well, I'm going to do unitary transformations at every k point, mixing at every k point those 4 bands. And so what I want to calculate is the gradient of the localization functional with respect to all possible infinitesimal unitary transformation at every k point. And remember, an infinitesimal unitary transformation can be written as do we have any? No. Can be written as an exponential of an infinitesimal anti-Hermitian matrix. Because remember, a unitary transformation is such that u dagger is equal to 1. So if you write exponential of A, where A is anti-Hermitian, or you could call it dA, or sorry, you could call it dW, exponential of dW, you do a Taylor expansion, is going to be 1 plus dW, and you do the transpose of that, and it's going to be 1 minus dW because it's anti-Hermitian. And so what we have is that to first order is going to be still unitary. So a unitary transformation, an infinitesimal unitary transformation, is just an exponential of an anti-Hermitian matrix. And so we actually write explicitly this transformation in our localization functional, and then take out dW, and we obtain a very complex expression that I won't go into detail, that is really the gradient of the localization functional with respect to this d omega. And then we can take just a steepest descent strategy, or a conjugate gradient strategy, in which we take steps in the opposite direction of the gradient, and those steps are all little unitary transformations everywhere in the Brillouin zone that sort of keep evolving my unitary matrices until this gradient is zero, that is, our object is as localized as possible. Luckily, you don't have to worry about this because it's all sort of hidden inside a code. The interesting part is that once this procedure is finished, what we actually find is that even if everything in our algebra is complex algebra, we find Wannier functions that are real. That was not evident at all. I mean, in a molecule, of course, you can always choose your orbitals to be real, and so the unitary mixing is going to be real. The orthogonal transformation, that is all what you need in a molecule, is going to be real. In this case, is not necessary. You can actually show that exponentially localized Wannier function are real. This is again this sort of recent work of 2 or 3 years ago. But you know what we are really doing here. We are not dealing with the tail of the Wannier function somehow. Our localization criterion focuses on the second moment. So I would say it's open for discovery why they should be real, but it's actually always the case. Or to be precise, it's always the case if your minimization is successful. What actually happens is that in general, the localization functional has many multiple minima, of which only one is the sort of physically intuitive and localized one, and a lot of them can be absolutely unintuitive and corresponds to sort of garbled Wannier functions that are not real and not localized. Or you can even have cases in which there are different and both physically intuitive states that are both real and localized. I'll try to comment on those. But so if you want, all this algorithm as a sort of key weakness, that is, we are dealing with a functional that has multiple minima. Things improve if you're working in the large supercell limit when you have only gamma sampling. Then it turns out that provided, again, for sort of fairly complex reason, you have only, say, either an orthogonal Bravais lattice, like a tetragonal orthorhombic or so on, or at the end you have only 6 B vectors that you use to define the differences. Say, if you are studying an FCC crystal, typically the reciprocal lattice of the FCC is BCC, so you'll do finite differences with 8 small vectors, and then that sort of introduces some kind of entanglement. But if you're doing finite differences using only 3 directions in space and not more than those, usually you are okay. But that's a sort of the difficulty, and the difficulty is really a topological difficulty that has to do with choosing these objects. I mean, remember, what we are going to do is we are going to evolve the possible phases or the possible unitary matrices in front of each of the U vectors. And we are trying to do this in 3 dimensions, and what it turns out is that the operations that we are going to do is such that this field, if you want, this matrix M between periodic part of the Bloch orbitals at every k is as smooth as possible. If you actually do theory of Fourier transform, sort of the properties of your Fourier transform, like the smoothness or the existence of discontinuities, are related with the decay behavior in the Fourier transform. So any kind of discontinuity sort of breaks down localization. And so what we are trying to do is make things as smooth as possible over all the Brillouin zone. But as we sort of, in a 3-dimensional system, as we start making things smooth, and we start from a place and we try to make it smoother, we can easily end up with a topological discontinuity. It's a bit like the problem of combing a sphere. I mean, if you are not careful, well, in the sphere it's always impossible, but you can make everything smooth everywhere, but end up with a single point where there is a divergence. And so there is a little bit a problem like that. That is, there is always a smooth choice that you can make, but depending on where you start, you might make things locally smooth, but end up with a topological problem. And there are sort of very effective way to sort of, in practice, avoid this problem that have to do with really giving sort of very basic, very coarse starting guess for what your Wannier function should look like. And I'm showing here an example. Okay, suppose I'm trying to construct a Wannier function,